When the processor is executing a program and encounters an instruction relating to I/O, it executes that instruction by issuing a command to the appropriate I/O module. Three techniques are possible for I/O operations: programmed I/O, interrupt driving I/O, and direct memory access DMA. In the case of programmed I/O, the I/O module performs the requested action and then sets the appropriate bit in the I/O status register but takes no further action to alert the processor. In particular, it does not interrupt the processor. Thus, after the I/O instruction is invoked, the processor must take some active role in determining when the I/O instruction is completed. For this purpose, the process periodically checks the status of the I/O module until it finds that the operation is complete. With programmed I/O, the processor has to wait a long time for the I/O module to be ready for either reception or transmission of data. The processor, while waiting, must repeatedly interrogate the status of the I/O module. As a result, the performance level of the entire system is severely degraded. An alternative known as interrupt driving I/O is for the processor to issue an I/O command to a module that then go on to do some useful work. The I/O module will then interrupt the processor to request service when it's ready to exchange data with the processor. The processor then executes the data transfer as before and then resumes its former processing. Interrupt driving I/O, though more efficient than simple programming I/O, still requires the active intervention of the processor to transfer data between memory and an I/O module, and any data transfer must traverse a path to the processor. Thus, both of this form of I/O suffer from two inherent drawbacks. First, the I/O transfer rate is limited by the speed with which the processor can test and service a device. And second, the processor is tied up in managing an I/O transfer. A number of instructions must be executed for each I/O transfer. When large volumes of data are to be moved, a more effective and efficient technique is required: direct memory access DMA. The DMA function can be performed by a separate module on the system bus, or it can be incorporated into an I/O module. In either case, the technique works as follows. When the processor wishes to read or write a block of data, it uses a command to the DMA module by sending to the DMA module the following information: whether a read or write is requested, the address of the I/O device involved, the starting location in memory to read data from or write data to, and the number of words to be read or written. The processor then continues with other work. It has delegated this I/O operation to the DMA module, and that module will take care of it. The DMA module transfers the entire block of data, one word at a time, directly to or from memory without going through the processor. When the transfer is complete, the DMA module sends an interrupt signal to the processor. Thus, the processor is invoked only at the beginning and end of the transfer. The DMA module needs to take control of the bus to transfer the data to and from memory. Because of this competition for bus usage, there may be times when the processor needs the bus and must wait for the DMA module. Note that this is not an interrupt. The processor does not save a context or do something else. Rather, the processor pauses for one bus cycle, the time it takes to transfer one word across the bus. The overall effect is to cause the processor to execute more slowly during the DMA transfer when processor access to the bus is required. Nevertheless, for a multiple word I/O transfer, DMA is far more efficient than interrupt driving or programmed I/O. An SMP can be defined as a standalone computer system with the following characteristics. 1. There are two or more similar processors of comparable capability. 2. These processors share the same main memory and I/O facilities and are interconnected by a bus or other internal connection scheme such that memory access time is approximately the same for each processor. 3. All processors share access to I/O devices either through the same channel or through different channels that provide paths to the same device. 4. All processors can perform the same functions, hence the term symmetric. 5. The system is controlled by an integrated operating system that provides interaction between processors and their programs at the job, task, file, and data element levels. Points 1 to 4 should be self-explanatory. Point 5 illustrates one of the contrasts with a loosely coupled microprocessing system, such as a cluster. In the latter, the physical unit of interaction is usually a message or complete file. In a SMP, individual data elements can constitute the level of interaction, and there can be a higher degree of cooperation between processes. An SMP organization has a number of potential advantages over a uniprocessor organization, including the following. Performance. If the work to be done by a computer can be organized so that some portions of the work can be done in parallel, then a system with multiple processors will yield greater performance than one with a single processor of the same type. Availability. In a symmetric multiprocessor, because all processors can perform the same function, the failure of a single processor does not hold the machine. Instead, the system can continue to function at reduced performance. Incremental growth. A user can enhance the performance of a system by adding an additional processor. Scaling. Vendors can offer a range of products with different price and performance characteristics based on the number of processors configured in the system. It is important to note that these are potential rather than guaranteed benefits. The operating system must provide tools and functions to exploit the parallelism in an SMP system. An attractive feature of an SMP is that the existence of multiple processors is transparent to the user. The operating system takes care of scheduling of tasks on individual processors and synchronization among processors. Figure 1.19 illustrates the general organization of a SMP. There are multiple processors, each of which contains its own control unit, arithmetic logic unit, and register. Each processor has access to a shared main memory and the I/O devices through some form of interconnection mechanism. A shared bus is a common facility. The processors can communicate with each other through memory, messages, and status information left in shared address spaces. It may also be possible for processors to exchange signals directly. The memory is often organized so that the multiple simultaneous accesses to separate blocks of memory are possible. In modern computers, processors generally have at least one level of cache memory that is private to the processor. This issue of cache introduced some new design considerations. Because each local cache contains an image of a portion of main memory, if a word is altered in one cache, it could conceivably invalidate a word in another cache. To prevent this, the other processors must be alerted that an update has taken place. This problem is known as the cache coherence problem and is typically addressed in hardware rather than by the OS. A multi-core computer, also known as a multi-chip processor, combines two or more processors, called cores, on a single piece of silicon called a die. Typically, each core consists of all the components of an independent processor, such as register, arithmetic logic unit, pipeline hardware, and control unit, plus L1 instructions, and data cache. In addition to the multiple cores, contemporary multi-core chips also include L2 cache and in some cases L3 cache. The motivation for the development of multi-core computers can be summed up as follows. For decades, microprocessor systems have experienced a steady, usually exponential, increase in performance. This is particularly due to hardware trends such as an increase in clock frequency and the ability to put cache memory closer to the processor because of the increasing miniaturization of microcomputer components. Performance has also been improved by the increased complexity of processor design to exploit parallelism in instruction execution and memory access. In brief, designers have come up against practical limits in the ability to achieve greater performance by means of more complex processors. Designers have found that the best way to improve performance to take advantage of the hardware is to put multiple processors and substantial amount of cache memory on a single chip. An example of a multi-core system is the Intel Core i7-5960X, which includes 6 x86 processors, each with a dedicated L2 cache and with a shared L3 cache. Please look at figure 1.28. One mechanism Intel used to make its cache more effective is prefetching, in which the hardware examines memory access patterns and attempts to fill the cache speculatively with data that's likely to be requested soon. Figure 1.20b shows the physical layout of the 5960X in its chip. The Core i7-5960X chip supports two forms of external communication to other chips. The DDR4 memory controller brings the memory controller to the double data rate DDR main memory onto the chip. The interface supports 4 channels that are 8-bit wide for a total bus width of 256 bits for an aggregated data rate of up to 64 gigabits per second. With the memory controller on the chip, front side bus is eliminated. The PCI Express is a peripheral bus. It enables highest speed communications among connected chips. The PCI Express links operate at 8 GT per second, transfers per second. At 40 bits per transfer, that adds up to 40 gigabits per second. Summary of Chapter 1.